Hello friends, I have discussed nearly free electron model in detail. While nearly free electron model is very useful for qualitative understanding of effects of periodic potential on electron in a solid, nearly free electron model is not generally used to calculate electronic band structure. There are several methods available to calculate electronic band structure. Such methods vary in terms of accuracy, speed, and computational cost. In this lecture, I am going to introduce a very simple method widely used for electronic band structure calculation, the tight binding method. In nearly free electron model, electron is viewed as a gas of nearly free conduction electrons, weakly perturbed by the periodic potential. EK curve of nearly free electron is very similar to free electron energy dispersion near the zone center. And effect of weak perturbation by periodic potential is visible only near the Bragg planes marked by the red dashed vertical lines in this figure. Tight binding model starts from a completely different point of view. It treats the solid as a collection of weakly interacting neutral atoms. For example, take lithium atom. It has 2 electrons in 1s orbital and 1 electron in 2s orbital. If the atoms are far apart from each other in space, energy levels of the orbitals are same as the atomic energy levels corresponding to 1s and 2s orbitals. However, as we move the isolated lithium atoms closer to each other, atomic orbitals start to overlap with each other. As a result, electron in an atom start to feel the presence of the neighboring atoms and the energy levels start deviating from the isolated atomic energy levels. In other words, from n isolated atomic energy levels, we get an energy band having n states. This is the 1s band and this is the 2s band. Each band has n energy levels. Width of the energy band depends on the overlap of atomic orbitals. For example, 2s orbitals overlap more than 1s orbitals. As a result, 2s band in lithium has larger bandwidth than 1s. Note that bandwidth is calculated at the equilibrium separation. Thus, this is the width of the 2s band, which is much larger than the width of the 1s band. Note that tight binding model deals with a case where overlap of atomic orbitals is just enough, requiring correction of isolated atomic picture, but not strong enough, making the atomic description completely irrelevant. Tight binding model is not an ab initio method where we can get the energy levels from first principles. The model we are going to use is a parameter based model. The parameter is overlap integral denoted by T. You need not to know how to get T at this moment. It is sufficient to know that more the overlap between two orbitals, more will be T. If you think in terms of lithium atom, 2s orbitals overlap more, and T for 2s orbitals is large. On the other hand, 1s orbitals overlap less, and T for 1s orbital is small. Let us start with a 1D lattice. It is reasonable to assume that the electron cloud of the nth atom is overlapping with the electron cloud of the neighboring atoms, that is n-1th atom and n+1th atom, which are the nearest neighbors of the nth atom. When multiple atoms are present, the Hamiltonian takes the form of a matrix. Let us learn how to build the Hamiltonian matrix. Element of Hamiltonian matrix is expressed as H, M, N, which is written in this form. This defines the interaction between mth and nth atom. Now take the nth atom. It has two nearest neighbors, n-1 and n+1. Then the element of Hamiltonian matrix corresponding to the nth atom are H, n-1, n is equals to minus T, where T has the dimension of energy. Similarly, for the other neighbor, we have H, n+1 is equals to minus T. Hmn is equals to 0 for all m not equal to n+1 and for all m not equal to n-1, because there is no interaction other than the interaction between the nearest neighbors. If there is no interaction, those terms will be 0, and if there is some interaction between two atoms, those terms will be equal to minus T. Let us take some specific example. Let us assume that we have 10 atoms in the linear chain. In that case, the Hamiltonian matrix is a 10 cross 10 matrix as shown here. Let me mark each row and column of the matrix first. So this is column 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is row 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Select some atom, say the fifth atom. This is the row corresponding to the fifth atom, and this is the column corresponding to the fifth atom. This is the location of the fifth atom in the matrix. Atomic orbital of the fifth atom overlaps with the atomic orbital of the fourth atom. That is why this term is non-zero. Similarly, atomic orbital of the fifth atom overlaps with the atomic orbital of the sixth atom. That is why this term is non-zero. The atomic orbital of the fifth atom is not overlapping with any other atom. That is why the rest of the terms are zero in this row. Thus, in each row, we have two non-zero terms. The only exception is the first and last row. The first atom has only one neighbor, the second atom, because the first atom is located at one edge of the chain. Similarly, the last atom has only one neighbor, because the last atom is located at one edge of the chain. Thus, we have a 10 cross 10 Hamiltonian matrix. We have to diagonalize the matrix to get the energy eigenvalues and corresponding eigenfunctions. Let me show a Python code to construct the Hamiltonian matrix, get the energy eigenvalues, and also get the eigenfunctions. The code is going to ask for the number of atoms in the linear chain. M is the number of energy intervals for density of states calculation. T has the dimension of energy. I create the n cross n Hamiltonian matrix in this step. This is an array to store the values of density of states. dE is the energy interval for density of states calculation. Now I construct the Hamiltonian matrix. Take ith atom, say this one. This is the HI term. This term is HI plus 1, and this term is HI plus 1 I, and both of them are equal to minus T. This is what I am defining here. This line calculates the eigenvalues and eigenvectors of the Hamiltonian matrix. W holds the eigenvalues and V holds the eigenfunctions. Then we find the density of states by calculating number of energy eigenvalues in a given interval. Finally, we plot the EK diagram. We plot the 10th eigenfunction and plot the density of states. This is the Python code to get the energy eigenvalues and energy eigenvectors of a 1D lattice. You are already familiar with NumPy and Matplotlib library. I have added one new library for the linear algebra calculation. This is going to be used for calculating the energy eigenvalues and energy eigenfunctions. This is where the code asks for the size of the chain. That is, you have to enter the number of atoms in the linear chain. M is the number of intervals for DOS calculation. The Hamiltonian matrix is defined here. This is the array for storing density of states. This is the energy interval for density of states calculation. This is the loop to create the Hamiltonian matrix. This is where we are finding the eigenvalues and eigenfunctions of the Hamiltonian matrix. This is where we are calculating the density of states. Finally, we plot the energy dispersion. We plot the wave function and we plot the density of states. Let us plot the ground state wave function. The code is asking for number of atoms in the linear chain. Let us enter 2000. This is how the energy dispersion looks like. This is the plot of the ground state wave function. Note that it has no nodes as expected, and this is the plot of density of states for a 1D chain. Let us plot some other wave function, say the first excited state. Again, let us enter 2000 and run the code. So this is the first excited state wave function, and you see that there is only one node. Now let us do for 10th excited state. Let us enter 2000 and this is the plot for the 10th excited state eigenfunction. From our code, we obtain the energy dispersion and density of states for a 1D lattice having 2000 atoms. We have used T equal to 1 and the band minima and band maxima has a value of minus 2t and plus 2t. The width of the band is equal to 4t. The width is defined as the range of maximum and minimum energy in the band. It can be shown analytically that the energy dispersion relation is Ek is equals to minus 2t cos k, and the density of states is equal to 1 divided by Em square minus E square, where Em square is equals to 4t square. Analytical results are plotted in A and B. It matches very well with what we obtained from our Python code. Note that in our code, we have plotted Ek only for k greater than 0. While for the analytical plot, Ek has been plotted for positive as well as negative k values in the first billowing zone. We also have plotted the energy eigenfunctions using our code. This is the plot for the 10th eigenfunction from the code. We can verify whether it has 10 nodes or not. Node 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Thus, the wave function indeed has 10 nodes. Note that the first zero of the wave function and the last zero of the wave function are not counted as nodes, as they happen as a consequence of a fixed boundary condition. Let me give you a simple tight binding recipe which can be easily implemented to take into account nearest neighbor interactions as well as beyond the nearest neighbor interactions. Later, this recipe is also going to help us to switch to higher dimension like 2-dimension and 3-dimension. Step 1. Select a row. Diagonal element in the nth row corresponds to the nth atom. For example, let us take the 5th row. 1, 2, 3, 4, 5. Diagonal element in the 5th row corresponds to the 5th atom. Step 2. Identify the nearest neighbors of the nth atom. In case of 1D lattice, this is the n-1th and n+1th atom. Enter -t in n-1th and n+1th column of the nth row. For example, take the 5th atom. 4th and 6th atom are the nearest neighbors of the 5th atom. So, we take the 5th row and we go to column 4 of the 5th row. 1, 2, 3, 4. So that means this is the column 4 of 5th row and this is the column 6 of 5th row. And we enter -t in both the places. Remember that t is a parameter given to us and t depends on overlap of atomic orbitals of the nearest neighbors. Now we can extend the model to include the next near neighbor interactions. To do that, we have to identify the next near neighbors of the nth atom. In case of 1D lattice, this is the n-2 and n+2th atom. And we have to enter -t dashed in n-2th and n+2th column of the nth row. For example, again, let us take the 5th atom, this one. Now, the 3rd atom and the 7th atom is the second near neighbor of the 5th atom. So, we select the 5th row and we go to the 3rd column of the 5th row and enter -t dashed. Similarly, we go to the 7th column of the 5th row and enter -t dashed. Since t depends on overlap of atomic orbitals, t dashed has to be significantly smaller than t. We can modify the existing code to include next nearest neighbors. Let me do that. If j equal to I plus 2 a ij equal to minus t1 a j I equal to minus t1. The value of t1 I have chosen to be equal to 0.02. Now let us run the code and plot the energy dispersion relation. So the code is asking for the number of atoms in the chain. So let me enter 2000. This is how the energy dispersion looks like. Let me enter a larger value of T1 so that you can clearly see the effect of second near neighbor interaction. So let me enter T1 equal to 0.2 and run the code. So again we enter 2000. So this is how the energy dispersion looks like. Comparing the plots of energy dispersion for different values of next near neighbor interaction, we find significant difference when T dash become comparable to T, as shown in the third figure. EK curve becomes flatter near the top of the band. Moreover, in case of T dash equal to 0, the spread of the band is symmetric about 0. So this is the zero energy. Maximum value of energy in the band is +2 and minimum value of the energy in band is -2. However, in case of T dash equal to 0.2, the spread of the band about 0 is no longer symmetric. The maximum value of energy in the band is 1.5 and the minimum value is -2.5. However, note that T dash equal to 0.2 is a very high value for a 1D lattice. For T equal to 1, T dash should be much smaller than 0.2.